Okay, so let me continue with the one of the last slide of the chapter 2. Okay, okay. Let me check it here. Here. Okay. So, quenching, tempering, and carburizing. Carburizing. Uh, in Vietnamese, thấm carbon. So the purpose of performing carburizing is to improve or to enhance the carbon content of the surface layer together with just to support the quenching process in order to form the magnesite on the surface layer. So the reason is that for those steel with the carbon content smaller than 0.3% of carbon, there is no possibility in order to quench. Yes, and therefore and the idea is that they want to create a steel structures so that in the centers or in the core of the material is soft, has the ductility and has the good ductility and large uh, percentage elongation. However, on the surface, they would like to have something which is hard and has a high hardness and has the ability to withstand the scratch and wear resistant. And in such a case, they apply the carburizing for the steam with having smaller than 0.2% of carbon. So after performing the carburizing process, the amount of carbon content on the surface layer can reach 0.7 up to 0.8% of carbon, and the surface layer can be quenched in order to form the magnesite structures, which can significantly improve the wear resistance and the strength of the surface layers. So there are several types of carburizing. So for example, in pipe carburizing, the steam can be heated above the A3 temperature. So you can see A3 here. Mhm. In cell metal box containing charcoal, uh, than, and barium carbonate. So the oxygen when react with the carbon in order to form the carbon monoxide, and then diffusing the carbon into the surface austenite layer. Mhm. And this can be used for enhancing the carbon content on the surface layer of the large components. With respect to regarding the gas carburizing, you steam heat up the materials with the steam having smaller than 0.2% of carbon above A3 temperatures in furnaces or in carbon-rich gas environment to promote the diffusion of carbon into the surface austenite layers. And the last but not least technique is to use the sun bath carburizings, meaning that you heat up the pot in the bath of carbon-rich suns. So you see that you can mainly use the sodium cyanide, cyanure, so it's quite detrimental to whole human health. In order to promote the diffusion of carbon and nitrogen from the molten sun into the pot, so they have the positive effect of the hardened microstructures with a thin layer of high carbon contents. However, please remember that you work with sodium cyanide group, and therefore is quite terrible for health. And you may consider the safety hazards in working with the cyanide. And after the process, the other difficulties is regarding the removal of sun from the hardened parts. Yeah, how to remove the cyanide from the part is one of the issues that you need to consider. And may result in the large grain structures because you heat up for the carburizing. So it means that you provide the free give energies for the diffusion of different atoms, and therefore you promote the green growth process and reduce the strength of the materials. Yeah, and as a result, you may have poor impact properties, and you need additional heat treatment in order to refine the grains. So generally speaking, we can talk about the two-stage process. If the carbon content on the surface layer is different from the inner core. So the first one is to heat up above the A3 temperatures. So please remember that A3 temperature is the light temperatures, and the specific temperature depends on the specific composition or the amount of carbon content. So you have to consider the specific temperatures. But when we talk about A3 temperature, so it's a line. The temperature will be reduced as the amount of carbon content increase up to the eutectic point. You heat up, and the core will still have the low carbon content. And when you quench in oil, so only the surface layer having the only the surface layer can be quenched because it has the carbon content larger than 0.03. Because you know that after the carburizing process, the carbon content on the surface layer can reach 0.7 up to 0.8% by weight. And after the quenching process in oil, and on the surface layer, you have the coarse martensite, and inside in the core, you still have the fine grain because we do not quench the inside, the core inside. And within the second stage, you heat up about the A1. Yes. Because if you, let's say, if you perform the carburizing and enhance the carbon content up to 0.9%, it means that after the eutectic point or hyper eutectic still, and in that case, you just heat up above A1 and perform the water quenching process in order to refine the martensite on the surface layer. And afterward, you can perform the tempering process for relieving the internal stress. So that's what the thing that we can do with the carburizing process. Thế thì cái vấn đề ở đây của chúng ta là thấm carbon là để đưa cái lượng carbon tăng lên cho cái lớp bề mặt, bởi vì quá trình thấm này chúng ta không thể thấm từ bề mặt vào trong tâm được, đúng không ạ? Nó sẽ đi từ nơi có nồng độ cao đến nơi có nồng độ thấp. Và tất nhiên là cái môi trường thấm carbon sẽ phải là môi trường có lượng carbon cao nhất rồi, và bên trong chi tiết thì có lượng carbon nhỏ thì hiệu suất thấm nó mới cao được. Ở đây đối với các cái loại thép trước cùng tích mà có hàm lượng carbon tương đối nhỏ, ví dụ là nhỏ hơn 0,2% carbon, thì chúng ta cần thấm, bởi vì những cái loại thép này nó rất là dẻo, đúng không ạ? Chúng ta cần tăng cái độ cứng bề mặt để chịu ma sát, chịu mài mòn tốt. Thế thì khi thấm thì nếu mà cái lượng carbon mà tăng đến 0,7 hoặc 0,8%, thì khi mà tôi thì chúng ta nung lên đến cái trạng thái hoàn toàn austenite hóa, nói cách khác là trên nhiệt độ A3. Còn nếu mà lượng carbon là lớn hơn 0,9%, có nghĩa là thép sau cùng tích, thì người ta chỉ cần nung lên trên nhiệt độ A1 thôi. Tại sao lại thế? Bởi vì là các bạn biết là thép sau cùng tích là vốn dĩ là thép có nhiều carbon, và carbon nó nằm ở đâu ạ? Nó nằm ở trong cái cementite, phải không ạ? Fe3C, Fe3C. Thế thì nếu như chúng ta đối với cái thép sau cùng tích mà chúng ta nung lên trạng thái hoàn toàn austenite hóa ấy, thì cái cementite nó sẽ bị hòa lẫn vào trong austenite, và austenite nó lại là pha mềm, cho nên là khi mà chúng ta quench, có nghĩa là khi chúng ta tôi thép thì nó sẽ còn cái lượng austenite dư, nó sẽ làm giảm độ cứng của thép. Ngược lại, nếu mà chúng ta nung lên đến trên nhiệt độ A1 đối với thép sau cùng tích, thì ở cái điểm này nó cũng có austenite rồi, nó cũng có cementite rồi, thì cái chuyển biến của chúng ta là gì? Là từ austenite đến martensite và cộng với cả cementite nữa, thì cái độ cứng của nó là đảm bảo. Cho nên là không cần thiết phải nâng lên nhiệt độ trên cái nhiệt độ austenite hóa ở đây, hoàn toàn austenite hóa đối với thép sau cùng tích. Thế thì ở đây chúng ta có 3 dạng đúng không ạ? Chúng ta có pack carburizing, chúng ta có gas carburizing và sunbath carburizing. Lưu ý các bạn là đối với cái dạng thái thứ ba này chúng ta sử dụng natri cyanide thì cái này rất là độc đúng không ạ? Thì nó cho phép là thấm được cả carbon và nitơ luôn vào trong cái chi tiết để tiến hành làm cứng cái bề mặt. Tuy nhiên thì chúng ta biết là vì là chúng ta làm việc với cyanide cho nên là nó là cái vấn đề về mặt sức khỏe, an toàn lao động. Và cái việc loại bỏ các cái muối cyanide sau cái quá trình làm cứng chi tiết là cũng là một cái vấn đề mà các bạn phải quan tâm. Tuy nhiên là vì chúng ta cái quá trình thấm này thì chúng ta nâng lên nhiệt độ cao để nó có thể khuếch tán được các nguyên tử carbon đúng không ạ vào cái lớp bề mặt. Vì chúng ta nung lên nhiệt độ cao thì các cái nguyên tử khác nó cũng nhận được năng lượng tự do, nó cũng khuếch tán, nó sẽ có khả năng làm to hạt, và khi làm to hạt thì nó sẽ giảm bền chi tiết đúng không ạ? Thì đấy là cái effect còn lại mà chúng ta sẽ phải tìm cách để find cái trade off. Ngoài ra thì chúng ta có thể nêu về cái two state process. Nếu như cái lượng carbon content ở trên bề mặt thì nó lớn hơn rất là nhiều ở trong cái inner core. Thì như tôi có nói lúc nãy là đối với quá trình đầu tiên thì chúng ta sẽ nâng bởi vì là cái thép ban đầu của chúng ta nó có cái core, nó có cái lượng carbon thấp đúng không ạ? Thì chúng ta sẽ heat up nó lên ở trên cái nhiệt độ A3, bởi vì ban đầu trước khi quá trình thấm thì trước cái quá trình thấm thì nó có cái lượng carbon rất là thấp đúng không ạ? Lượng carbon mà nhỏ hơn 0,8% thì chúng ta sẽ tiến hành nung lên trạng thái hoàn toàn austenize hóa, có nghĩa là trên nhiệt độ A3 để ra fully austenize. Sau đó chúng ta tiến hành quench ở oil thì chúng ta sẽ có fine grain ở cái core, còn coarse mark tensile ở trên cái surface layer. Thế sau đó thì nếu như cái surface layer của chúng ta mà thấm và chúng ta đạt được cái độ cái lượng carbon lớn hơn 0,9% carbon hoặc là khoảng 0,9% carbon, nó thuộc là thép sau cùng tích rồi, thì lúc này người ta sẽ nung lên trên nhiệt độ A1 thôi, và chúng ta tiến hành là tôi bằng nước. Thì cái quá trình tôi này nó sẽ ảnh hưởng lớn đến cái lớp bề mặt thôi, còn ở bên trong thì nó vẫn giữ nguyên với cái trạng dạng hạt nhỏ mịn. Và vì chúng ta tiến hành hai quá trình tôi này cho nên là cái thép sinh ra sau cái quá trình mà xử lý nhiệt ấy nó sẽ rất là không ổn định, bởi vì tôi là cái quá trình mà làm nguội nhanh đúng không ạ, trạng thái ứng suất dư lớn. Do đó là chúng ta sẽ phải tìm cách khử cái trạng thái ứng suất dư này bằng cái quá trình ram thép ở cái nhiệt độ thấp thôi, để tránh cái hiện tượng là làm to hạt. Yes, that's the end of the second chapters. So do you have any other questions? Further readings I have suggested you to read in order to understand what have mentioned on the slides. So it's not easy to understand all because there are several information which did not mention here. So for example, the crystal structure of metals, there are BBC, FCC, and ACP, which were not included on the slide. Defects in the crystal structures, for example, the void defects in metal, impurities, or others, especially dislocation, because we have talked about the density of dislocation. The strengthening of metals, as you may remember, we talked about the solid solution strengthening. We talk about work hardening. We talk about precipitation hardening and others. More on the binary phase diagram, there are several rules, but I have just mentioned about one type of diagram is the iron carbon binary phase diagram, and we do not consider the whole range of the carbon content, but just limit to the 0 up to 6.67% of carbon, because it's corresponding to the poly of cementine. With the higher amount of carbon content, the steel or the cast iron is extremely brittle, and we did not find the application for this material practically. And phase transformation, we talk more about the cooling process, where the austenite can be transformed to the for example, pectide, if we have the slow cooling rate in order to promote the diffusion process. With the high cooling rate, the austenite can be transformed to bainite, or if the cooling velocity or cooling rate is higher than the critical cooling rate, and then we have um, the transformation from the austenite to the martensite. And please remember, this is uh, the process is not complete, and you have some kind of residual austenite after the transformation. So, and together with a different kind of heat treatment, we also talk about the carburizing or nitriding, but nitriding was not mentioned here. The carburizing is mean that we how can I say, we heat up and to the part inside the carbon-rich environment in order to promote the carbon diffuse into the surface layer of the materials, so that we can enhance the amount of carbon content on the surface layers. Yes, in doing this, the surface layer has high amount of carbon content, and generally speaking, harder than the inner core of the materials. So that on the surface is the part can withstand, can resist good wear, uh, wear resistant and scratch resistant, but inner core is relatively ductile and has great percentage elongation and can withstand the impact load well. Yeah, that's the point. Okay, so now I would like to stop the second chapter. So if you do not have any other questions concerning the ferrous alloys, and we can turn into the third chapter, we will focus on the non-ferrous alloy. So for example, copper alloy, aluminum alloy, nickel alloy, titanium alloy, and others. Where is it? Sorry for all the edit. So let me open the chapter 3. Okay. So aluminum and aluminum alloys. So I think this is the popular material that almost all of you familiar with. And we also study in at high school, I think. For when we talk about non-ferrous alloys, it means that those alloys which do not contain the iron inside the materials as the base element. For example, even inside the aluminum, you can still detect a small amount of iron, but it's not the base element. This is some kind of impurity inside the aluminum alloys, for example. So, but with the small amounts, and therefore you could say that is not the base element. Similar to the other case, for example, copper alloy and titanium alloys, which has very small amount of iron inside and consider as the impurities, or we can consider iron not as the base element. Concerning the pure aluminum, the density of around 2.7, 10 to 3 kilogram per meter cubic. You know that aluminum is weak, very ductile material, and has very good electric and even thermal conductivities. The electric conductivities of aluminum is equal to two-thirds of that of the copper. So aluminum is easy to react with oxygen. So in air, especially at high temperatures, the oxidation reaction can occur rapidly between the oxygen and aluminum to form the thin layer of oxide called alumina on the metal surface to protect the aluminum from further attack by the oxygen. Does it mean that on the outer surface layer of aluminum part, you will have the alumina, and inside is aluminum, for example, or aluminum alloy. This means that on the outside surface, you have alumina showing very good corrosion resistance. Very good corrosion resistant. So for sure, aluminum has high thermal conductivities, but had non-magnetic natures and high reflectivities, which means that when you irradiate laser onto the aluminum, uh, the small amount of heat or the laser will be absorbed by the aluminum, and the other will be reflected, and therefore it's quite very hard to melt the aluminum material by the laser because of high reflectivity. And that is one of the reasons that we is a little bit difficult in order to sinter or to additively manufacture the aluminum alloys by additive manufacturing. Aluminum is among the important materials. Mhm. And can be used to fabricate important aerospace structures. And because I mean, it's not the poor aluminum, but aluminum alloy. Yeah, because it's light and is have very good strength. And this can be used to fabricate, for example, fuselage, empennage, the wings in Boeing 737, 747, 757. Yeah, or the Airbus. Yeah, is quite famous. So it's quite famous airplane, Airbus A320 or A340. And on the right side, you can see that the how can I say the figure that this describes the use of aluminum alloys in Boeing 747 on aircraft. And aluminum is account for 68% of material on these of these aircraft. Yes. So composite is just account for 17%, but now it's increased for composite up to 50%. Sorry. The reason that aluminum is commonly used for aerospace structures, seem, is are, for example, is had moderate cost. So cost is important factor that affect the decision of whether or not we use aluminum or other materials. Ease of our fabrication, except for additive manufacturing. Yeah, it can be relatively easy in order to fabricate the part, the aluminum part by casting or forging. But then, if you want to additively manufacture the aluminum part, so it's a little bit more difficult comparing to other materials, since aluminum has high reflectivity. Lightweight for sure. It just 2.7 is mean that the density is about one third of steel. One third of steel. High specific stiffness and strength, sure. Good ductility, yeah. Fracture toughness and fatigue resistance. So ability to resist crack when subject to the cyclic loading. And good control properties by mechanical or heat treatment. Yeah, yeah. With the development of technologies, yeah, we can we have this part for many metals, not only aluminum. Yeah, and everything has two side effects, and aluminum is not an exception. And we still have some disadvantages of using aluminum alloys in aircraft structures. For example, aluminum has low mechanical properties at high temperatures. Because at high temperatures, it can be softened, especially after above 150 degrees C. Uh, Aluminum is susceptible to stress corrosion cracking. And when aluminum come into contact with carbon fiber composite, so we may observe the corrosion. We can observe the corrosion, yeah, because we have two different types of materials. And if we have the solvents, we containing the ions of two different metals, and it can promote the corrosion process. Edge hardening alloy, hardened alloy can not be easily wetted. Yes, yeah, these the physical properties of yeah. But now we have different joining processes, not only wetting process, in order to join together uh, materials. But generally speaking, yeah, this is one of the disadvantages of using aluminum alloys in aircraft structures. Not easy to be wet, especially for those edge hardened alloy. So regarding an alloys, you see that aluminum can be alloyed with different metals. So for example, zinc, magnesium, copper, aluminum copper. Yes, is quite famous. Edge hardening alloys. Yes, for example, as a part inside the ferrous alloy steel, and we have talked about the precipitation hardening. And I took one example, not regarding steel, but precipitation hardening. So I have shown you about the aluminum alloys with 4% of copper. Yeah. And aluminum can be alloyed also with magnesium. I'm sorry, manganese and silicon. Especially aluminum and silicon is called casting alloys because aluminum combined with silicon can form the eutectic point. Generally speaking, eutectic point is the point has lowest melting temperature, so very easy to be cast because you need lower energy to heat up the material up to the melting, up to the molten state. And manganese. Yeah. So here you can also classify aluminum based on the alloying elements. So you have the edge hardening alloys when aluminum alloy with is alloyed with copper or magnesium, magnesium and silicon, and zinc and magnesium, and so on. But of course, on the next few slides, we will talk about the classification for the aluminum and aluminum alloys. I'm sorry, for aluminum alloys. And mechanical properties of aluminum for sure depend on purities, of course. When impurity occurs, so it rarely affect the mechanical properties of aluminum, but it depends on the specific alloying element. Amount of work, yes. So it means that we apply work hardening process or not. Because generally speaking, once you have the work hardening process, you can break the large grain to form the small grain. The number of grain is increased, meaning that you have increased the grain boundaries regions, and therefore you improve the strength, improve the hardness. But on the other side, you reduce the ductilities of the material. So that's why I always ask you to be careful. Yes, because you need to find the trade-off between the hardness, the strength, and the ductility. The presence of small amount of alloying elements can improve tensile strength and hardness of the material considerably. Yes, so this is the effect of adding alloying elements. Even the small amount of alloying elements can significantly modify properties of the material. Yeah, yeah. The development of aluminum alloys for aerospace structures, yeah, rely on the strength, improvement of static strength, fracture toughness, resistance to crack growth, damage tolerance, and stress corrosion. And that's why I would like to remind you several times about the ductilities, because one, the material has high ductility, and then you can have good damage tolerance, because when the impact force is applied to the part, and then the part can be deformed. And once the airplane land on, and then you can change the part. So it means that the part can work for a certain period of time before replacement. But if it does not have the damage tolerance, it means that under the influence of the impact force, the part is suddenly broken down. So significant, the terrible the issue will be occur. And yeah, you see the consequence of low damage tolerance, fracture will occur, yeah, immediately, and then block the engine, for example. What happened afterwards? And thread corrosion. Okay, yeah, it's good. Okay, great. You still remember that you need to check your attendance at 2:30. It's great. But starting from next week, we will meet each other at class. So yeah, it's not an issue for the class of aerospace materials, but keep doing this for the class of yes, additive manufacturing. And regarding the additive manufacturing, I will speak to you a little bit more detail on the Thursday. Uh, however, for the course of additive manufacturing, we have only 8 days. Yeah, and the last days contain only 2 teaching hours, so it means that 100 minutes. And as a result, I don't think that we have enough time to let you have a small test at I mean the midterm test. Yeah. So I'm thinking about the fact that I let you answer one more question during the final examination, and take it as the midterm test mark. Yeah. But for the course of aerospace material, it's up to you. It's up to you to select the form of midterm test. Whether you answer one more question during the final examination, or you can do the test in the next 2 weeks, for example, if you want. Okay, so where am I? So classification. So there are several types of aluminum alloys. For the casting alloys, of course, this can be used for casting. Yeah. So generally speaking, the properties of casting alloys are poorer than the wrought alloys. And basically, we do not use the casting alloy, I mean aluminum casting alloy for aerospace structures, because it has a poorer mechanical and even chemical properties comparing to the case of wrought alloys. Poor surface quality as well. But they are grouped among the other type of aluminum alloys, so we need to know. Uh, the first is the heat treatable cast alloy, like for example aluminum, copper, magnesium, and these are the base elements. But we can add other alloying elements as well, and can be subjected to the solution treatment and edge hardening. Yeah, solution treatment and edge hardening. The second type is the non-heat treatable cast alloy. For example, the aluminum silicon. It can be used to cast. It means that we can cast by sand casting or decasting, and it can be used in automotive industry like gearbox, radiators. I would say that an example that is not mentioned here is the piston head, yeah, which made of aluminum silicon, piston head, radiator, hộp tản nhiệt, radiator, gearbox, hộp số. Yeah. The Roche alloy, heat-treatable Roche alloy. This means that after performing the rotting process, you can apply the heat in order to modify the properties of the alloy. So typically we have the system containing the aluminum, copper, magnesium, zinc, and silicon. Uh, and the properties can be improved by work hardening or plastic forming. So you use the plastic deformation in order to improve mechanical properties of the alloys. Like for example, using the extrusion process, drawing or rolling. Uh, extrusion, drawing kéo qua, rolling là cán cuộn. Plus heat treatment, yes. And after the process of plastic forming, and then you need to heat treat to release the residual stress. Or you may form the precipitates, yeah, to increase the strength, the performance of the materials. And nearly all aluminum in our craft structure belong to this category, the heat treatable Roche aluminum alloy. And the other type is non-heat treatable Roche alloy, yeah, which is, for example, aluminum, magnesium, manganese. So when we apply the heat treatment, and the properties of the Roche aluminum alloys almost do not change. Uh, Properties do not change. The type of alloys has high ductility, good corrosion resistance, and with these properties, and these non-heat treatable Roche alloys can be used for making the utensil, tube, or other type of marine applications. And regarding the application in aerospace, since the non-heat treatable Roche alloy has relatively low strength, low fatigue resistance, and is the non-heat treatable Roche alloys are not widely used in the aerospace industry. So although the material show low strength, but we can improve the strength of the non-heat treatable Roche alloy, not by heat treatment, of course, but can be done by solid solution strengthening or strain hardening. So as you can see here on the right side of this slide, for example, this is the binary phase diagram of aluminum and silicon. And when we, how can I say, consider the composition of 20% of silicon and 80% of aluminum, you see that here. You can reduce the temperatures of eutectic point, and therefore you save the energies for heating the material up to the molten stage for casting process. Yes, because aluminum silicon is the cast aluminum alloy. Yeah, but actually we have many cast alloys. It depends on the specific composition that can be used. For example, 1% of silicon, 99% of aluminum, and others. Okay. So here you could see the table. I just divide the table into two parts so that it can be fit into the slides. So this show you the typical properties of different aluminum alloys based on the classification that we have dealt with. We have the composition, the conditions, Condition is mean that different heat treatment processes can be applied in order to modify the properties, for example, tensile strength, elongation, percentage elongation, or the hardness of the materials. In the case of roch, non-heat treatable alloys, so yeah, we alloy with the manganese or magnesium with a certain composition, and we can use anneal process. Anneal is mean quá trình ủ, but during the second chapter, we do not focus on the annealing process for the steel, but you can read it at home if you are interested in. Okay. So for the anneal, it means that perform the heat treat, some kind of heat treatment, and you do not have the significant effect because this is the non-heat treatable alloys. It means that even if you apply heat treatment, yeah, it's okay to apply, but if the strength is not improved, and then why should we apply? Yeah, it wastes money, time, and effort of the technician. Yeah, and hard, you can improve with the H8. You can improve the tensile strength, but then you reduce the elongation percentage. Yeah, that's what you need to balance. So to focus more on the heat treatable rod alloys because it can be used in aerospace industry as we have talked about. So yeah, there's several options that we could have. So for example, in the case of 4% copper is quite famous. Yeah, 4% of copper, so more than 95 because you have something like magnesium, silicon, and manganese. So 95, 94. And you can have the precipitation hardening process, which can significantly improve tensile strength. Yeah. With respect to the case of non-heat treatable rod alloy, you can see that that is the why heat treated alloy, rod alloy aluminum can be used for aerospace industry because, yeah, it's almost 4 times higher than the tensile strength of non-heat treated rod alloys. Yeah, that's the reason. And at the same time, you can somehow uh, let's say maintain a reasonable value of percentage elongation, so 20%, comparing to the case of just 3%. Yeah, in the case of alloying with 1.25% of manganese. Yeah, so it's a reasonable values for the percentage elongation. When you perform the heat treating process for the rough aluminum alloy in order to how can I say, to have the precipitation hardening effect. That's what I would like to highlight. And for the cast, so you have a two type, non-heat treatment alloy and heat treated alloy. So basically, with heat treated alloy, you can improve properties by precipitation hardening. Solution hardening, yeah, can also improve the strength of the material, but slightly improve. But with precipitation and hardening, you can significantly improve the strength of the material because you know that we have the second hash phase well dispersed within the matrix. We can retard or we can prevent or reduce the movement of dislocation inside the material and therefore improve mechanical properties of the materials. Yeah, you can even alloy with the nickel, so 2% of nickel, 4% of copper, and 1.5% of magnesium. Yeah, it's quite interesting to know about this because 2% of nickel is not high, but this is an expensive material, so that's why I'm interested in. Okay. So let's talk a little bit more about the heat treatment for the aluminum and aluminum alloys. So when we talk about heat treatment and we pay more attention to the group of heat treatable rod alloy, yes, because it can be used for aerospace industry and is by using heat treatment we can improve properties of that materials. So aluminum and copper, for example, especially duralumin with 4% of copper, 0.8% of magnesium, 0.5 of silicon, and 0.7 manganese, and the compensate amount of aluminum. Yeah, so that we have 100% of by weight of the materials. So this material is widely used in aircraft bodywork, and for the heat treatment, there are several steps, including solution heat treatment, quenching, and etching. So somehow, like in the case of ferrous alloy steel, and you also have solution treatment, quenching process to have the super saturated solid solution, and then etching, yeah, in order to form the fine precipitate particles dispersed well in the matrix material and improve mechanical properties of such materials, of such a material. So we talk about the specific duralumin material, and for the solution treatment, we need to heat up the material up to 600 degrees C, and typically within the range of 450 up to 600 degrees C. We hold for long enough time, yeah, and then dissolve uh, the alloy elements or precipitates in the aluminum matrix. So to have the fully unfast structures. So any precipitate like the theta phase, copper alumina, uh, copper aluminide, sorry, will be dissolved in the unfast. So to have the fully unfast structures. Mhm. And then you maintain for a certain period of time so that the dissolving process happen completely. And once the dissolving process uh, complete completed, and then you can perform the rapid cooling step in order to quench the materials. Yeah, this means that you rapidly cool down the material at these temperatures in order to form supersaturated solid solution of copper inside the aluminum matrix. However, after the quenching aluminum materials, yeah, the material is soft and ductile, because here we do not have the magnetite structure for sure. You know, here we do not have the magnetite structure. You have magnetite is the supersaturated solid solution of carbon inside the ferrite. But here you have only aluminum and copper, or the theta phase here. And therefore, after the quenching aluminum materials, duralumin, for example, you still have the soft and ductile materials. However, we at this stage we do not let the part work. I mean that we subject the part to the manufacturing process in order to shape the part. So if you want to shape the part to a certain geometry, and this is a good time to do because it's soft and ductile, so it's easy to be formed, to shape into the final product. And afterwards, we perform the artificial etching process in order to improve mechanical properties or the strength of the materials. The aim of the process of etching is to transform the supersaturated solid solution to precipitate particles. The particles here is typically the copper alumini. Yeah, the copper CuAl2. This can be done by heating the quench material up to 200 degrees C, and typically in between the range of 150 and 200 degrees C. And yeah, here I just noted about a series of chemical and microstructure transformation in order to improve the strength. So you know that initially you have the copper cluster inside the aluminum matrix, and then the copper cluster in front of the disc will be grow, and then you have the GP zone, and the GP zone will distort the matrix, but still have the link with the lattice structure of aluminum alloy surrounding, and the distortion of lattice structures will create will improve the strength of the materials until 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 the point we have the incoherent precipitate. This means that the precipitate is no longer share uh, the lattice structure with the aluminum surrounding. In that case, we have the reduction of the strength. So once we have the ZP zone, and the ZP zone will uh, put will place the elastic strain surrounding aluminum matrix, and prevent the movement of dislocation, or you can say resist the dislocation slip, and therefore improve mechanical properties of the duralumin. So here we can see the the effect of changing etching temperatures on the properties of the aluminum alloys. So when you perform the natural etching process at room temperatures, so you see that the time to enhance the properties of aluminum alloys is long, is pretty long. So it takes more time in order to enhance the properties. And the hardness improvement is relatively low with respect to the other case when you perform the artificial etching at higher temperatures. So for example, 165 or 300 degrees C. So the higher the temperatures is applied in order to etch the aluminum alloy, the faster the hardness improvement, the faster the process of hardness improvement. So what we need to pay attention to is the amount of time and the temperatures, so that we can reach the highest point of the hardness for the aluminum alloys during the artificial etching process. Because above this point, we have over etching, and then the strength or the hardness will be reduced. And then how to find this point is a critical thing. You need to test, you need to perform experiments in order to find this point for a certain materials. But higher the temperatures, the faster the process, and also the faster the reduction in the strength. So that's why you need to find the relevant time and temperatures for the artificial etching process. For the purpose of properties improvement regarding the aluminum alloys. Nói một cách nôm na theo tiếng Việt thì khi mà các bạn consider cái hợp kim duralumin này, thành phần chính của nó là nhôm và 4% copper, ngoài ra thêm một vài các cái thành phần khác. Thế thì quá trình đó là cái quá trình mà chúng ta heat up để tạo ra cái tổ chức thuần túy là alpha, có nghĩa là nếu như cái cấu trúc ban đầu nó có sẵn cái second half phase ở đây, là copper aluminum 2 ở đây thì nó sẽ bị hòa tan vào trong cấu trúc alpha để tạo ra cái tổ chức alpha thuần túy thôi. Sau đó người ta duy trì trong một thời gian là để cái quá trình hòa tan này được diễn ra hoàn toàn. Thế sau đó, đúng không ạ? Thế sau đó thì người ta sẽ tiến hành quenching, có nghĩa là tiến hành tôi cái tổ chức nhôm này bằng cách là tiến hành làm nguội nhanh với vận tốc lớn hơn hoặc bằng vận tốc tới hạn. Thì khi đó người ta sẽ tạo ra một cái dung dịch rắn quá bão hòa của đồng trong nhôm, đúng không ạ? Tuy nhiên là khác so với thép, là cái dung dịch rắn quá bão hòa của đồng trong nhôm ấy thì nó lại không cứng, bởi vì nó không có tổ chức mắc tensile. Ngược lại thì nó rất là mềm, rất là dẻo, cho nên là sau khi tôi cái nhôm này thì nó lại ra được một cái tổ chức mà nó phù hợp với quá trình tạo hình cho chi tiết, có nghĩa là gia công áp lực để tạo hình chi tiết đến một cái hình thù người ta gọi là final product. Thế thì sau khi mà tạo hình được chi tiết rồi thì chúng ta sẽ phải tìm cách làm tăng bền cho nó để đưa nó vào một cái ứng dụng thực tế. Thì người ta sử dụng cái biện pháp là hóa già nhân tạo, hoặc là hóa ra tự nhiên, có nghĩa là để ra ngoài tự nhiên thì nó cũng tăng bền thôi. Tất nhiên là tăng bền đến một cái mức độ nhất định, nếu nó bắt đầu thải bền đi thì độ bền nó sẽ giảm xuống hoặc là độ cứng nó sẽ giảm xuống. Tuy nhiên là nếu mà để hóa ra tự nhiên thì cái thời gian diễn ra hóa ra nó sẽ rất là lâu, như vậy là cái productivity hay nó cái năng suất của cái quá trình nó sẽ rất là thấp. Thế cho nên người ta mới quan tâm đến quá trình hóa ra nhân tạo, có nghĩa là tiến hành nung lên một cái nhiệt độ nhất định để thúc đẩy cái quá trình hóa ra, đúng không ạ, để tạo ra các cái pha rắn nhỏ mịn phân tán trong cái cấu trúc của nhôm, nhờ đó mà tăng bền cho nhôm. Chủ yếu là tạo ra cái pha CuAl2 này nó phân tán, nó nhỏ mịn mà nó phân tán trong cấu trúc của nhôm để từ đó tăng bền cho nhôm. Thế cái cơ chế của việc tăng bền thì các bạn biết là cơ chế Oro-1 lúc nãy tôi có trao đổi. Lưu ý với các bạn là cái chính của chúng ta là phải tìm ra cái nhiệt độ và cái thời gian để mà chúng ta tìm được cái maximum, cái cực trị của cái quá trình tăng bền này. Bởi vì quá thì nó sẽ bắt đầu diễn ra cái quá trình thải bền. Nhiệt độ càng cao thì tăng bền nhanh nhưng mà thải bền cũng nhanh, cho nên là mà lại tốn cái nhiệt lượng, đúng không ạ, tốn nhiều năng lượng, nó gây ra cái hao phí trong cái quá trình mà chúng ta chế tạo, dẫn đến là tăng giá thành. Tuy nhiên thời gian dài, thời gian là tiền bạc, thời gian cũng là cái mà các bạn phải cân đối, cho nên là phải cái trade off giữa cái nhiệt độ cũng như cái thời gian để tiến hành quá trình hóa ra để đạt được cái maximum về cái hardness, là cái mà các bạn là cái mà các cái kỹ thuật viên hoặc các cái nhà nghiên cứu về vật liệu người ta tiến hành. Yes, I think that I try to finish this slide, and on the next week we will continue with the next slides. And please remember, check your attendance with their messages, and then I'm still here until 3:35, to answer any of your questions that maybe arise. Especially if you have any question regarding the the assignments that you need to complete and submit at the end of this semester. So 1 week after I finish the lecture, that you need to pay more attention to. And please remember that you need to submit both the file and the hard copy. The file can be submitted through the monitor of the class, and the hard copy you need to submit to me when after you answer the questions, after you ask them during the offline meeting. Okay, and this slide just to highlight the mechanism of heat treatment to promote the precipitation hardening process. To promote the precipitation hardening. So here you have, remember that you perform the solution heat treatment in order to create the complete alpha phase, and then you quench in order to perform the supersaturated solid solution of copper inside aluminum matrix, and then you shape the part before you perform the second step of heat treating, called artificial etching process. And at the beginning of the artificial etching process, you will have the formation of the cluster zone or the Greener Preston zone. It means that the copper atoms will be arranged randomly in the lattice structure of aluminum and we call GP1 or theta 2 prime. Let's go like this. And by increasing the time for the etching process, the copper atoms will be arranged in an order pattern, but still have the connection with the aluminum matrix, and we call it coherent with the aluminum matrix. And in such case, we have the uh, we still have the theta 2 prime. Yeah. And we have the reduction of the strength only. Uh, I think something is something inverse because coherent is here and incoherent is here. Yeah, I see some issue here. Coherent có nghĩa là có liên kết với cả cấu trúc mạng, và incoherent có nghĩa là không liên kết. Trước đó thì các bạn sẽ tạo là GP zone, sau đó là coherent, sau đó nó phát triển thành một cái hạt độc lập thì nó mới sẽ thành cái incoherent ở đây và nó giảm cái strength. Cho nên là cái đồ thị này thì có thể là các bạn xem xét lại, không cần phải refer đến cái đồ thị này, không refer đến. It's taken from Introduction to Aerospace Materials, so I don't know why it's like this. So let me open the okay. So there's no need to open this one. Okay, let me continue the slide first. Okay, this is how the precipitate particle grow. We have nucleation site of GB2, and then we have the heterogeneous nucleation. So nothing special. Cái tạo vùng GP ở đây là theo cơ chế sinh mầm và phát triển mầm khi mà các bạn tiến hành cái artificial etching. Cho nên ở đây có đưa đến cái vấn đề là mầm tự sinh hay còn gọi là homogeneous nucleation và mầm ký sinh hay gọi heterogeneous nucleation. Cái này chúng ta cũng không cần thiết phải đi quá sâu vào. Tôi cũng có đề cập với các bạn một lần về cái mầm ký sinh và mầm tự sinh, nhưng mà chúng ta không cần thiết phải đi quá sâu. So when the intermediate precipitate reach the final compositions and create the structure unchanged stable, upon on further etching, and then we have the equilibrium, it means that is here. Yes. And the maximum properties is when the precipitate transform to coherent to the incoherent. So it means coherent is something here. Yeah. Yeah, transform. And then we have the reduction in the strength. Yeah. I think this diagram is incorrect. And further etching, so we have the reduction in the strength. We increase the size of equilibrium particle. It means the particle growth. The large grain size means that you have the reduction in strength and hardness. Yeah. And resulting in the softening when the over etching occurs. Yeah. Correct. So what I would like to highlight here that please remember when you perform the precipitation hardening by the artificial etching process, initially you have the GP zone. It's the copper atom cluster to form the disk of copper atom inside the aluminum matrix. Yeah, and this distorts the lattice structure of aluminum matrix surrounding, and then we improve slightly the strength the materials. But once the ZP zone is grow, and we have the precipitate grain, but the grains is still coherent with the lattice matrix and distort the aluminum matrix, and then you have the considerable enhancement of the strength up to the maximum point here. And we have the reduction in strength when the precipitate is incoherent with the surrounding matrix. So just changing the position of coherent and incoherent here on the bottom right side of the slide. And therefore, it's critical to find to stop the etching process once you have the incoherent precipitates in order to have the maximum heat strength of the material. And that's what I would like to say. Yes, and let me check again about the I think here. This is here. Yeah, this mean is coherent. So you have the connection between the theta 2 prime phase with the surrounding aluminum matrix, and incoherence. This means that you do not have the lattice linking. Mm-hmm. Yeah. Yeah, it's somehow here. You have it coherent here and incoherent here. Yeah. So please remember that. Yeah. Stop sharing. So please pay a little bit attention to the slide that I have shown you, because it's not correct. It's incorrect. It's incorrect. Yeah. This one is incorrect because first we have the coherent and then incoherent. Okay. And I think that's all for today. I think that's all for today. Before stopping and checking your tendon, do you have any questions? Okay. So if not, I just turn off my camera, mute my mic, and then check your tendon. And thank you for your attention, and wish you have a nice day ahead. And goodbye for now.